Fantastic, Caroline.
Hi, Yuanyuan. All right, fantastic. Dr. Yuanyuan Fan, I'll hand over to you now. Thanks.
Okay. Thank you so much, Caroline. Guys, I'm sure you can all see me from the video feed, but hopefully we can focus on the slides throughout the session. So welcome everyone to our Smart Grids session. I'm Dr. Yuanyuan Fan. I have electrical degrees from my bachelor's, master's, and a PhD. And I have been working on power systems pretty much in the last 10 years with some pure theoretical projects and some industry-based projects as well. I'm particularly interested in smart grids, especially how we, as engineers, handle the data from smart grids to make sure we really achieve a smart grid, not like a partially smart grid. So from here, I'll just progress to the technical content. Today, we will be looking at basically 4 sections. You can see we'll be looking at a brief introduction to smart grids. We'll be looking at renewable energy, which is apparently an essential part of smart grids. We'll be looking at what machine learning can do for our smart grids. In the end, I'll take you through a few case studies. Okay, let us first look at what is a smart grid. Here we have the traditional power grid. I'm sure all of us are very familiar with this system. Our market operators, I think I'll grab a pencil. Our market operators dispatch power from power plants. Then the power is generated, transmitted, and distributed, and eventually reach our customers. Most of us are customers, I believe. All of us, actually. All of us are on the consumption side, although even if we are really working in the power grids, we are still consuming power on a daily basis. We can see clearly from this power flow that it is one direction. It is a one-way flow of electricity. So what other characteristics are there for the traditional power grid? We can see clearly most probably the traditional power grid has centralized bulk generation. They are relying on fossil fuels such as coal and oil. There is a very limited automation. We need a lot of human intervene. There is very limited situational awareness as well. Most of the time, we do not know what's really going on in the power system. And also, as consumers, we lack data to manage the energy use from our side. For example, I have energy use that are not really urgent. I want to put the energy use at some particular time when the electricity prices are low, like my dishwasher, my washing machine. I want to use them at some time that can save me money the most. Or if you have solar power installed at your home, you want to use this kind of non-urgent appliances when the sun is up high. Okay. Now, apparently, traditional smart grids cannot do so. What do? Is we look at smart grids now. What's the difference? If we go back to the last slide again, we come back, we can see apart from the basic power infrastructure, we have communications as well. With communications, we can have a two-way power flow. Two-way power flow means our power can be from the major generation side to consumers, and it can be vice versa as well. Apparently, we also can accommodate renewable sources such as wind power, solar power, and even electric vehicles. The process apparently will deal with large amount of data analysis and data processing. We'll be looking at that shortly. So based on the comparison, let's give smart grids a definition. If you read some references, you will be able to see many different definitions for smart grids. Let's look at this super long one. Okay, it perhaps accommodates the majority of the information that a smart grid should have. It says a smart grid is an electricity network that uses digital and other advanced technologies such as cyber secure communication technologies, automation, and computer control systems in an integrated fashion to be able to monitor and intelligently and securely manage the transport of electricity from all generation sources. All generation sources to economically meet the varying electricity demands of end users. The end users can be households, can be businesses, can be the industry. The definition is quite long, but we can immediately extract a piece of information from this definition. What is that information? Smart grids is not a thing. It is not any specific technology. It is a concept, a vision. To understand it better, let's look at some characteristics of smart grids based on the functions we want to have. You can see we want our smart grids to optimize asset utilization and improve operating efficiency. We want the smart grid to accommodate all generation and storage options. We know nowadays energy storage is becoming more and more essential for our modern power grids. We want our smart grid to provide high power quality, to anticipate and respond to system disturbances. We want the power grid to be more resilient. We want to enable active participation by consumers. This is something related to demand response. If you have been keeping an eye on what's going on in the industry, as consumers, we want to participate in, for example, frequency control of our power grid. We want to enable new products, services, and markets. Okay, you can see from these characteristics, the mission to achieve smart grids is really not an electrical engineer's job. Sorry, I should say it is not just an electrical engineer's job. There are so many areas that, well, we have to include to make sure we can realize smart grids. You can see I have listed a few areas here. We might be looking at asset management, telecommunication, instrumentation and control, power conversion, electric vehicles, HVDC FACS, renewable artificial intelligence, and so on and so on. These days, we talk about interdisciplinary skills. It is apparently impossible for one person to become super knowledgeable, super experienced in every area, such as listed here. But it is very important that we have one focused area. For example, if you are an electrical engineer, you want to have some general idea about the rest of the areas, such as artificial intelligence. You want to know how artificial intelligence can help in your power system operation. If you are just an electrical engineer, you try to interact with, for example, a data engineer or a data scientist. You two can communicate to achieve excellent results, no doubt about that. However, when you have the knowledge of both data and electrical engineering, you will definitely have a more in-depth understanding and more in-depth analysis and perhaps more successful accomplishment. Okay? Now let's talk about renewable energy, which is an essential part of smart grids. You can see on the right side, I have the non-renewable energy. These are very common to us: oil, coal, nuclear, natural gas. We know these are not great. We want to achieve renewable energy as much as possible. On the left side, I listed some typical renewable sources: wind, hydro, solar, geothermal, and biomass. Okay, we know clearly the first three, wind, hydropower, solar, are perhaps the most installed renewable energy so far in our power grid. There's one more source, one more energy source that is not listed here. It is hydrogen, H2. Okay, I didn't list it here because hydrogen, if you talk about the way you produce hydrogen, it can be renewable, it can be non-renewable. We'll look at it shortly. Okay, basically, we will mainly look at the dominant renewable power at the moment, which are solar and wind. We'll also be looking at hydrogen briefly. Hydrogen is not very popular at the moment, but definitely it is one of the most promising energy sources. It is actually also a means of energy storage, but we'll look at that shortly again. Now let's look at solar. With solar, we actually can utilize two ways to get power out of it. One way is the way that we have seen like almost everywhere. It is PV. We use PV cells or PV panels to convert sunlight into electricity. This is how our rooftop solar systems work. Another way is CSP. CSP is mainly for centralized generation, concentrated solar power. What does it do? It actually converts the sun heat into electricity. So when you have a CSP, still you will be using a steam generator or steam turbine. Okay, so this is CSP. It is more on centralized power generation, but for PV, it can be distributed or centralized generation. Let's look at some beautiful pictures. Sorry, the next slide is beautiful pictures. This slide doesn't have that many pictures. Before the beautiful pictures, let's look at what a typical PV system includes. There must be solar panels. This is a way that we can convert sunlight into electricity. There should be an inverter, because we know the power output from solar panels is EC. We want AC power. There should be a battery to store excess solar power, or if the load power is very high, the battery can supply the power as well. Ideally, there should be a solar tracker, so our solar panels can always face the sun. And apparently, there are accessories as well. Now let's look at these beautiful pictures I mentioned earlier. On the left side, we can see we have rooftop solar. Clearly, from the picture, the rooftop solar is not installed on one particular side, not north, not south, but on two sides, in two directions. The purpose is perhaps one set of solar panels like this one, maybe facing the sun in the early morning, and the other set of the solar panels, which is the majority part, they may be facing the sun around noontime. This way is to produce as much solar energy as possible. Clearly, we can see when we have solar panels installed on more than one side of your rooftop, most probably you do not have a battery. If you have a battery, you perhaps want to install all solar panels on one side. Which side? The side that is facing the sun during noontime or around noontime. Only in that case can you produce the maximum power, and you can store your power in your battery. In Western Australia, where I am based in, most probably the households do not have a battery. So this is actually a very typical arrangement you will see if you come to, for example, Perth. Now let's look at the middle part. This is a solar farm. It is apparently much larger. This is a centralized generation. As I told you, PV can be used for distributed or centralized generation. Clearly, the left side, regarding the rooftop solar, we know it is distributed generation, and the picture in the middle shows us an example of centralized generation. We can also see solar farms, they are taking a lot of land space. This is not something that can be possible in the long term, because the land on Earth is apparently limited. So what do? We move further to offshore, which gives us the right side picture. Offshore solar panels. Now let's look at wind farms. For wind power utilization, we also have onshore and offshore wind farms, just like solar. Further, in recent years, people are actually looking at floating wind turbines. If you look at the picture on the right side, this is a picture of floating wind turbines. Floating wind turbines are not in commercial use at the moment, but definitely we can look into that further, because as time goes by, we will use up all the land, and we cannot always stay close to shore, which is about 50 to perhaps 200 meters from shore. We have to go down deeper in the water or further in the water. Okay, so it is really valuable to do some initial research at the moment. Now let's look at the wind turbine at a closer distance. I'm sure if you have visited some wind farms, most probably onshore wind farms, you have seen wind turbines like this. Okay, now what can we see? What are the main parts of a wind turbine? We have a base, okay? We have a tower to support the turbine blades and all the systems. We have nacelle. Then, of course, we have turbine blades. What is in the nacelle? The main components are the gearbox and the generator. Sometimes the gearbox and generator are located at the base. Okay? Here, I want to show you the idea of how big a wind turbine is. If you have not seen a wind turbine in real life. Okay? GE's General Electric 12 megawatts wind turbine called Haliade wind turbine, Haliade X, hopefully I'm pronouncing it correctly. It has a height of 260 meters. imagine how tall it is. The rotor diameter is 220 meters. This wind turbine is one of the largest wind turbines around the world. Just last month, Vestas, another very popular wind turbine manufacturer, launched an even larger wind turbine. How big? 15 megawatts. You can see the sweeping area is equivalent to about the 6 football fields, so it's really huge. Let's have a look at a picture. This is a wind turbine blade. I'm sure we can all see. This is a wind turbine blade. Can you see how big it is? I don't know what manufacturer this one is from, but it is a typical one, I believe. So it is really huge. Now, let's think about this. Why do we have these large wind turbines? Do we just want to manufacture really large wind turbines to show off? To show, you see, this is how big I can go. Is it just to show off? No, it is not show off. Let's look at the formula of wind power. Wind power is equal to half rho A V W cube CP. What is rho? Air density. A, cross-sectional area. VW, wind speed. CP, rotor efficiency. Okay, now if we look at this formula, we will quickly have an idea how to get the maximum power possible at a given wind speed. How? It is related to the air density. With the air density, there's nothing much we can do. Of course, we want to increase it, but unfortunately, we do not have superpower. So air density is out of the consideration when we try to increase power. We'll just use whatever is there. A is a cross-sectional area. It is equal to pi rotor diameter square. Okay, can you see now? This is where we got the idea. This is where we got the idea to increase the rotor diameter. In other words, to increase the length of the turbine blades, such that A is increased. Of course, PM is increased. Okay, please pay attention to here. Now, VW, how do we increase wind speed? Again, not much we can do, but we can definitely go to areas that have higher wind speeds. Like where? We can move from onshore to offshore. When it is offshore, there is no tall buildings, no tall trees. Definitely, we will have a more steady and higher wind speed. So this is one of the reasons that we want to go to offshore. Of course, limited land space is also a reason. Now, at the end, we have CP. CP is the rotor efficiency. To improve or to increase the rotor efficiency or to maintain the rotor efficiency at the maximum possible, we actually need to implement Mppt. What is Mppt? It is maximum power point tracking. Okay, how do we do this? To achieve Mppt, we actually have to achieve an optimal TSR. For each given turbine blade, the optimal TSR is also a constant. It's always a constant. So if you receive a wind turbine from manufacturer, your optimal TSR is fixed. if you can achieve and then maintain this optimal TSR, then you will be able to achieve your Mppt. Okay, what is TSR? TSR is very easy to understand. T, tip, S, speed, R, ratio. Tip speed ratio, okay? Tip speed ratio. TSR is equal to omega m. Omega m, which omega m is the blade rotating speed, times RB, the radius of rotor blades, over wind speed VW. Apparently, your rotor blades, they are there, so RB cannot change. The only way we can maintain an optimal TSR is to maintain a fixed ratio between omega m and VW. That is how we get the idea that our turbine rotating speed needs to follow wind speed. So your wind turbine shouldn't be rotating at a fixed speed if you want to achieve Mppt. Okay. Now let's look at how Mppt is implemented. Apparently, we need power converters. By controlling the firing angles or turning on angles of our electronic devices in the power converters, for example, IGBT, we can control the power that we achieved from the wind side. Let's look at the right side, which will give us a better idea about Mppt. The top curve we have here, or top curves we have here, is from induction generator, SCIG, squirrel cage induction generator, which is a fixed speed generator. The bottom is from DFIG, doubly fed induction generator, which is a variable speed generator. Let's look at the top graph first. You can see there are black dots. These black dots are all labeled as MPP, which means maximum power points. Because the fixed wind turbine is always operating at the same wind speed, what happens is, let me grab a red pen. What happens is, let's use W equals 0.8 pu. What happens at this wind speed? The maximum power that we can capture is here. It's about 0.5 pu. However, because the wind speed, generator is operating at 1 pu, we can only capture 0.4 pu of wind power. So we are not utilizing the wind energy as much as possible. To utilize our wind energy as much as possible, what do? If only we could follow all these black dots. Can we? Yes, we can. Okay, yes, we can. This is how we are using Mppt. Let's look at the bottom graph. Doubly fed induction generator. This is a variable speed generator. It can operate at different wind speeds. Different rotating speeds. Look at this. 1, 2, 3 different rotating speeds, so that at every wind speed, no matter it is your VW3, VW2, VW1, it always captures the maximum power points, these ones. Okay, so this is the idea of Mppt. DFIG is actually the most popular option in the industry at the moment. There are other types of variable speed generators as well. For example, PMSG, which is a synchronous generator. It's called permanent magnet synchronous generator. This is very expensive due to the use of permanent magnets, but it can go popular in future. Okay. With solar, of course, we have Mppt as well. Solar Mppt and wind Mppt are a bit different, because with the solar Mppt, what do is, with each temperature and radiation, you look at the voltage and current curve. Your voltage current curves will give you the power curve, because power is equal to voltage times current. If you look at the curve on the left side, you can see you will be able to achieve the maximum power point at certain voltage value and current value. This is why we have to constantly adjust our voltage and current levels to make sure we follow our maximum power points. The idea of Mppt controller from the converter side is the same. We control the firing and angles, turning on and even turn off angles of the power electronic devices like IGBT. Okay, you can see clearly electronics are so essential in the control of renewable systems. Now, after discussing solar and wind, let's look at some data. I put this data here because I think it is very important. It is urgent as well. This is not a very technical slide at all, but I would hope to share this information with everybody. You can see the graph on the left side is the year 2100 warming projections. If we look at the right side, following our current policies, the temperature rise will be by about 2.7 to 3.1 degrees by the year 2100. This is pretty high. Our famous Paris Agreement told us we have to control the temperature rise within 1.5 degrees. How can we do so? If we look at the green curve, this is what we can do. We have to greatly decrease the carbon emission. We have to change our policies. When you look at the right side graph only, you can see from 2016 to 2020, the wind power installations across the world is generally increasing. Especially in 2020, we got 93 gigawatts. This is huge. Looks like it is a huge achievement. However, it is not really optimistic at all. According to the CEO of the Global Wind Energy Council, we are supposed to install 180 gigawatts power, renewable power. Sorry, I think this data is perhaps for wind power only, per year to get to where we are supposed to be to meet the Paris Agreement. When we installed 93 gigawatts in 2020, that was already a lot. But when we look at the target here, really, we have fallen behind. We have to work even harder to increase the renewable installation to make sure we will have a sustainable future. Now, let's look at hydrogen. I mentioned hydrogen can be renewable or non-renewable. Why is that? There are different ways of producing hydrogen. We can produce hydrogen from renewable sources like solar, like wind, by splitting water. In this way, you will get your hydrogen and oxygen. no pollution, no carbon emission, very good. However, nowadays, due to costs, hydrogen is mainly produced from coal, natural gases. In this way, you can see clearly there will be carbon emission. You might want to use carbon capture storage technology to bury the carbon, but it is not a long-term plan. Personally, I do not think we should spend a lot more effort on carbon capture and storage. I think we should perhaps focus more on the hydrogen production through renewable sources. This is a sustainable way. This kind of hydrogen is called green hydrogen or renewable hydrogen. If you get your hydrogen from coal, from natural gas, you will get what people call brown hydrogen. Okay. Now, apparently, a very typical use of hydrogen is to use fuel cells. We use fuel cells so we can produce electron flow, which of course can power our load. However, most of the time, the electrolytes are very expensive, very, very expensive. This is one of the reasons that fuel cells are not that popular. This is unfortunate. Hopefully, I think these areas could be something that chemical engineers can work on. Okay. Now, let's look at hydrogen stations. Why do we talk about hydrogen stations? If you have read through some data, you will know the very majority of carbon emission is from transportation rather than from the power sector. Transportation takes about half of the carbon emission. Our power sector accounts for about 40%. The rest are other sectors such as buildings. So many countries, especially European countries, start from transportation. We start from transportation by utilizing hydrogen. From the left side, you can see we have a development of hydrogen refueling infrastructure worldwide graph. Each year from 2010 to 2019, you can see the hydrogen stations are generally increasing. And then if we look at the data by region, you can see apparently the green one and the blue one, they are trying very big effort. They are making very big effort and improvement in hydrogen utilization. What is the green one? European countries. Blue one, Asia. NA, the green bars, is not applicable. It is North America. If we look at that, it is not really increasing. Look at the red line I just drew. It is not really increasing. This is a little bit unfortunate, but I think it is mainly due to the policies. Okay. Now look at the rest of the world. ROW, so small. Most countries do not see hydrogen as a very good option, mainly due to the cost. And we also know if we look at electric vehicles, all the electric vehicles, or I should say the majority of the electric vehicles are based on batteries, lithium-ion batteries, rather than hydrogen fuel cells. Okay, now let's look at what else can we do with hydrogen apart from powering vehicles? We can directly burn hydrogen in heating and cooking. In this way, we do not have to build new pipelines. We can use the existing natural gas infrastructure to transport our hydrogen. So this is really nice. I know in some parts of the world, perhaps not many, people are already using mixed natural gas and hydrogen for cooking. And also, we can generate electricity. We have seen the example of using fuel cells, or instead of using fuel cells, we directly burn hydrogen to generate electricity. And the last item is very interesting. We say we can use hydrogen as a means of storage. How do we do that? The most practical ways so far perhaps are to convert hydrogen in the form of ammonia, or compress hydrogen so it becomes a liquid. This is actually related to the concept of P2X. P2X. We'll be looking at that shortly. P2X is a new type of thinking or new concept for us to store power, for us to store energy. Before that, let's look at why hydrogen is not favored by most of the people. It has low density. People say it's too hard to compress. The cost is very high. If we want to generate green hydrogen or renewable hydrogen, it is too expensive. We have to use a lot of water. When we have seawater, we have to desalinate the seawater. Too expensive. Implementation, we have to most probably use fuel cells. When we have fuel cells, we have to use electrolyte, which is, again, too expensive. If we look at people commenting on hydrogen, perhaps you will notice all these disadvantages compared to other sources or other storage options like batteries. But I hope we do not get discouraged too much just because of this. We know when we look at about 40, 50 years back, electronics were very expensive. There was no way that we could implement concepts such as renewable energy integration. There's no way we could do power conversion. Now look at this. The costs have dropped. How much? I don't really have a number in my mind, but at least the use of electronics in power conversion in renewable systems is so common, so popular now. Okay, so that's why I say this is a very promising source, although it is not very popular at the moment. Now, talk about energy storage. We know energy must be produced and consumed almost at the same time. And we know batteries are the most popular choice at the moment. How about hydrogen? We have learned hydrogen. Let's look at how to use hydrogen to store energy for longer terms. This is where we have the concept of power to X. Our electricity can be used to for hydrogen production through electrolysis. And after we get that hydrogen, what do we do? As I mentioned, we can produce chemicals like ammonia or other chemical like methanol for industrial processes. This is called power to gas. So you can see this X can be gas. Or power to chemicals. This X can be chemicals as well. This point is perhaps not very attractive to us or not very interesting unless you are a chemical engineer. The second point may grab your attention. You can see it can be combined with captured CO2, carbon dioxide, and make carbon neutral liquid fuels such as crude, gasoline, diesel, and other fuels. Power to liquid fuels. So X can be liquid fuels. This can be used for transportation, for example. And then stored green electricity can do what? It can generate heat. So power to heat. Also, what else can it do? It can be transformed into electricity. Although it is essentially, it may be in some other formations, but it can be transformed into electricity, power to power. That's why we have the concept of power to X. We can use hydrogen as a means to convert our power into different types of resources, like chemicals. In this way, the electricity is actually stored. Okay? Now let's look at distributed generation. I know when we talk about renewable sources, no matter you're talking about wind or solar, most of the time you want to talk about distributed generation because you read so many papers, so many project reports from industry, from the academia about distributed generation. So let's have a introductory level idea about the distributed generation. Distributed generation is actually to generate power at the point of consumption. It is usually in small scales. The initial cost may be a little bit high, but you save costs from transmission and distribution. Distributed generation usually has renewable sources, and sometimes, or most of the time, there should be storage devices, most probably batteries. And as we mentioned, rooftop solar is a very typical distributed generation example. Okay, now let's come back to smart grids. We talk about renewable sources, we talk about hydrogen energy storage. Everything has to come back to smart grids. Of course, we know smart grids need to have these values. But what kind of implementation, what kind of, let's say, how to say this, what kind of specific applications we can develop based on the smart grid characteristics? When we said we can enable active participation from consumers, this is what we can do with demand response. We'll look at that shortly. We accommodate all generation and storage options, including the ones we just went through. We enable new products, services, markets. For example, we do peer-to-peer energy trading. We'll look at this shortly as well. We optimize asset utilization and operate efficiently. VPP could be a way to do that. VPP is virtual power plants. Basically, the concept is you have a geographically large enough area, you have your own power sources, perhaps you have some loads as well. You can participate in power system stability, maintenance, let's say you can support the stable operation of power grids by participating For example, frequency control, by participating in frequency control. And of course, we want to make some predictions. For example, we want to predict outage. So we are ready with what's going on in future. All of this have to come with data. We use sensors to collect data. We build communication infrastructures to make sure we can transmit our data so that we can build advanced control algorithm. We can send demands, send commands to our actuators. This is where we are touching the concept of machine learning. You can see already from this slide, smart grids needs machine learning. It cannot be smart without machine learning because we need to utilize the data. Machine learning is very close to artificial intelligence. If you ask a data scientist, perhaps they'll tell you machine learning is just artificial intelligence. They are the same. But some other data scientists may think, no, it's not. Machine learning and artificial intelligence, they are not exactly the same. Machine learning can learn from the existing data to make its own decisions, but artificial intelligence sometimes, or actually artificial intelligence most of the times has to be realized by explicit programming. So you have to program every single bit to tell it what to do. But machine learning does not need that. Machine learning, as we can see here, uses a variety of algorithms that interactively learn from the existing data to predict outcomes. Here are 3 types of machine learning techniques: supervised learning, unsupervised learning, reinforcement learning. Supervised learning is basically when you have the data with labels. You can, that means you have some, perhaps some features, and you have one column 1, 2, 3, 4. You have different columns of features, and in the end, in the last column, you have the labels. So based on any coming future coming in features, you can produce a label. For example, if a machine will fail or not. This is supervised learning. It can be classification. It can be regression as well. For unsupervised learning, the most typical application is clustering. Okay, clustering. What do we do? Clustering is very popular in anomaly detection. For example, here at EIT, we have a software called Iris. It is a invigilation software for the students to do exams. It is possible to use the clustering algorithms to detect which students conducted plagiarism. Okay, which students had plagiarism. How does it work? Perhaps you have various data of a student's exam process. You will be able to group them into different clusters, but there's one point that is very far away from the other clusters. Maybe this point is different. Sorry, I don't know why I selected the same color. I'm supposed to select another color. This one point is perhaps the one that you should look at. This could be a plagiarism. Okay, so clustering is very important for anomaly detection. Reinforcement learning is actually when you do not have data, you really need your machine to learn from trial and error.
Yuanyuan, I'm just going to come in to your presentation. It's so informative. Thank you so much. Just before, because I know that we're looking at an hour time slot for most of the attendees in the session, so I'm just going to get my colleague Riley to send through the link to register for the certificate of attendance if anyone does need to leave a little bit earlier. But Yuanyuan, please continue on. It's a fantastic session, and there's quite a few questions coming through, so we may not get to each of them at the end, but if not, we can answer individually afterwards. So thank you.
Okay, thank you very much, Caroline. I'm sorry, I just felt very passionate about the topic.
No, no, please
overrunning.
continue, Yuanyuan. It's brilliant, so thank you.
Thank you, Caroline. Thank you very much, everyone. Okay, let's look at big data in smart grids. What kind of data do we have in smart grids? We have learned what we can do with data. Potentially, we can do machine learning. But when we talk about smart grids, we have internal data and external data. Internal data is basically the measuring data, like a PMU data of smart metering data, and so on and so on. You can see I have some examples here. External data is actually the types of data that are relevant or related to our smart grids, but they are from external sources, like weather data or electricity market data. So these are all data, there perhaps can be more, all the data that we can look at when we want to look at smart grids, when we want to realize smart grids. Now, I have a long list regarding what machine learning can do to make our power system smart. You can see we can do failure prediction, power outage prediction, demand management, even theft detection, predictive maintenance, and so on and so on. All these are actually very popular in the research field from the industry or from the academia. And these items are not really exclusive. They can include one another. For example, failure prediction can include condition monitoring as well. All this would need the effort from the data experts. If you are an engineer and you are a data expert as well, then imagine how much you can do, how much potential you have to deal with all these issues. As engineers, we always should keep an open mind. We shouldn't just restrict ourselves within the engineering fields. We should look outside the area. Look at data engineering, look at data science. If we master more knowledge from the data side, we will be able to have a better understanding of these problems. We will be able to solve these problems and solve further problems or identify further problems. This is an example regarding demand side management or demand response. Demand response, basically, if you look at the energy operators' way of implementing it, they usually give consumers some incentive. So the consumers can participate in reducing their load or in feeding in more power to the power grid. Let's look at the right side. The right side is one scheme of demand response. We have a we have an energy operator. We have an end user. Here we also have DRA, which is a demand response aggregator. This aggregator is like a coordinator to coordinate the power flow between end user and AEMO. So end users, sorry, you don't have to worry about AEMO. It's Australian energy market operator if you are not based in Australia. Okay, between end user and AEMO, so we ensure the smooth participation from our demand side. Okay, here is an example of energy forecasting. Energy forecasting is very essential in demand response, so we can plan properly. This example basically tells us, apart from what we can collect what data we can collect from the power systems. We can also collect data from other means, like we ask our participants to do a survey regarding their lifestyles. With more information, we can make better predictions of the energy use. Now, the next example is peer-to-peer energy trading. Peer-to-peer energy trading is getting more popular, but still is not that much. It's very rare, unfortunately. But people would like to do peer-to-peer energy trading. The reason is when we sell our excess power from our rooftop solar, for example, to the power grid, we know the price is very low, a lot lower than the price we are paying to the power grid. Okay, that's why we might think, I do not want to sell my excess power from my solar panels to back to the main grid. I want to sell my power to another customer. This is where we got the concept of peer-to-peer energy trading. In peer-to-peer energy trading, we can have a broker which acts like a coordinator. Or in future, hopefully, I think this is the ideal scenario we will be looking at. We communicate with each other directly to decide if we want to buy power, sell power from others. Okay, in this way, we are more proactive to maintain our energy use. This paper actually is very interesting. I think you can take a read. It's from J. Kim and B. Lee. What it says is it compares energy trading with stock trading. It says for stock trading, what I do is I just want to make a decision at a time if I want to buy stock, sell, or hold. There are differences in electricity trading, though. We know electricity reserve can change in real time. For example, when my solar power is generating more, or my wind speed is very high today, then I can have more power in the electricity reserve. Or the other thing is, when we trade electricity, we know in the process of transmission, there will be power losses. So if you sell your power to someone close by or to someone who is, I'm not sure, 100 kilometers away, apparently, the power losses will be different when your power reaches to the customer side. Okay, so there are different things that you have to consider. This paper give an idea about how peer-to-peer energy trading can be done. This is apparently not the only way, but this is an example how machine learning can be implemented in peer-to-peer energy trading. Basically, it says, I just want to make a decision. Do I buy? Do I sell? Do I hold? Then it uses artificial neural networks, which is artificial neural networks-based reinforcement learning to give rewards when the decision is correct, or when the decision is considered a good decision. So in this process, you can control your buy, sell, or hold. This is a very interesting paper to give you an idea. However, please don't restrict yourself into this scenario. Try to be open-minded, read more papers. People may have easier scenarios or even more efficient scenarios for us customers, general customers, not electrical engineers or data scientists, to trade power. And the next example is regarding predictive maintenance. When we look at predictive maintenance, we want to start from data to define the machine learning problem. Whenever we have a machine learning problem, we have to define it properly. Otherwise, we cannot get it done. You can see on the left side, I have some data. Right side, I have some data. Apparently, the left side data has a column called date. So these are timestamps. The left side data is called time series data. The right side is not. The left side is actually from some household consumption data. energy consumption data. The right side is from a power plant. I don't recall what this data mean exactly already, but this gives you an idea what time series data is like. This is essential because if you have a time series data, when you do your machine learning, you want your recent time stamps to be your test data. You have training sets. Training set, you have a test set, you want a train and a test split to follow the timeline. But when you have non-time series data, you can just randomly select your training set and data set, test data set. And also after the data inspection, you want to look at what algorithms you should use. I'm sorry, I think I'm in a little bit rush due to the time constraint. Let's look at supervised and unsupervised learning, or unsupervised learning. Okay, do we use supervised or unsupervised learning? Apparently, we have to look at if we have the past failure records or not. If yes, most probably we want to use supervised learning. And when we want to use supervised learning, we do not want to go for unsupervised, because when evaluate the accuracy of unsupervised learning, it is not that straightforward. And if it is supervised learning, do we look at classification or regression? It depends what you are trying to do. That's why it's so important to define a machine learning problem. If you are using classification, maybe you are trying to look at a certain period, like 6 months or 1 year. Will your equipment fail or not? So it's a yes or no question. That's why it is a classification. And when you look at regression, what happens is you might want to look at the remaining useful lifetime of your equipment. So you will get some number like 6 months, 1 year, 24 months, whatever. So this is a regression problem. You need to know what you want. Okay, and if you have unlabeled data, you can do clustering to find where you might have some potential failure from your equipment. Let's look at some graph. This is an example of doing predictive maintenance or condition monitoring using a machine learning algorithm called dbScan. If you look at the left side, this is not time series data, but clearly based on the clusters, you can tell the blue dots are perhaps the anomalies, because they do not belong to any clusters. And if you look at the right side, this is a time series application of dbScan. So at this timestamp, perhaps you have got some problem. Okay, you can see machine learning is clearly very important in predictive maintenance as well. Apart from the examples we have given in demand response, in peer-to-peer energy trading, in predictive maintenance, what else can we do using machine learning? We can do a lot more. I have listed some here. We can do predictive control. We can analyze participants' survey. For example, we have a new smart grid strategy that we just implemented. We want to know how the participants feel like. We can do that. We can do a survey, and there will be text data. You can use natural language processing, which is NLP, to analyze your test data to see what's going on. Is the strategy really satisfactory or not? You can optimize your power flow to ensure the minimum power losses. And you can also take images of your equipment using algorithm called convolutional neural networks, CNN, to define how your equipment is going, what the condition is like, and so on and so on. I'm sure as engineers, we can think a lot more. Now let's look at some case studies. The first case study is regarding a project, I think based in UK. It's called the Dolphin Project. What it does is, this is just a prototype, by the way. It's not in any large scale. Okay, what it does is, you can see it has a floating wind turbine, which is floating in the deep water. You have an electrolyzer unit. What you do is, you desalinate the seawater to get clean water, and then through the electrolyzer unit, we get hydrogen. And apparently, in the electrolyzer unit, we have to use electricity to split water into hydrogen and oxygen. That's why solar is participating here as well to generate electricity. Okay, this looks really fancy. When I just saw this project, I really I felt it is mind-blowing. It is converting renewable power at the site to hydrogen, and then transmit hydrogen out through pipelines. And if you want, you can transmit part of the energy in the form of electricity as well. So it can be a combination of electricity transmission and hydrogen transmission. It can be only hydrogen as well. Okay, this is one case. Now the second case is regarding the Hornsdale Power Reserve. And when people hear about Hornsdale Power Reserve, maybe it's not that familiar, but it is just the giant battery in South Australia. Okay, the one that is built by Tesla. This graph and this data is actually from the Hornsdale Power Reserve official website. So basically, you can see I have time series data. I have different prices. Please pay attention. FCAS is frequency control ancillary services. When we talk about FCAS, it can regulate power at normal operation, and it can regulate power when there is a power outage as well. In this data particularly, it means regulation. Okay, FCAS lower means you perhaps need some. If your frequency is lower, that means you have too much load. So you perhaps need to increase your generation. Okay, you may dispatch some power from some generators, and you say, okay, I pay you this much. Please give me some power so I can regulate my frequency. This is what it means. Please have a look at this official website to get more information. It's very interesting. The last one is regarding the work of a master thesis student from EIT. What this student did was he actually combined the hydrogen, wind, solar, and the battery, and built a entire system. He also used the traditional generators. I think this is a diesel generator. Apparently, this system looks very complicated, but the student designed this problem based on real data from a particular region. This is what is available in the region, and this guarantees the lowest cost. Okay, I think that is all from me. I'm very sorry for overrunning the session, guys.
Thanks, Yuanyuan. That was brilliant. Thank you. I could see so many people still stayed on after the hour slot, so that's brilliant. I just wanted to raise, there were a few questions that were popping up, but because of the time frame, what I might do is I'll probably collate the questions together and get you to respond to them, and we can go out individually to those people, if that's okay.
Yeah, and that's a good idea, Caroline.
Fantastic.
Sorry, Caroline, for overrunning.
No, you were awesome. Just before we wrap up, Riley, my colleague, has sent through the link to the certificate of attendance. So please fill that out, and we will be sending that certificate of attendance out. You will receive that within the next week. and we will be sending the recording out along with the presentation slides. So a huge thank you, Yuanyuan. That was an extremely informative presentation, and I'm sure you're reading the comments. Everyone found it extremely beneficial, and a huge thank you to you, Riley, for joining us and helping answer the questions popping up in the chat box. As always, if anyone's got any questions, you can reach me on that email address on the screen. And when you do receive the email from us with the recording, please feel free to respond with any comments or questions. Thanks, Yuanyuan, and have a wonderful evening. And thanks all for joining us today.
Thank you so much, Caroline, Riley. Thank you, everyone. Bye.